Hello everyone, good evening. Welcome back to your own YouTube channel, Wallah English. Okay, I hope everyone is doing great. Till last class we have covered precipitation. We have discussed the entire chapter of precipitation, and today we are going to start abstraction from precipitation. I hope you are all are doing great. So, before starting, everyone kindly comment that I am fully audible and visible to you all. Then we'll begin our lecture today. It will be very interesting for you all to know. Okay, so I am expecting that till now sound is less. Okay, wait a second. Hello, I think sound is good. Good evening, Sushil, Vishal, everyone. Good evening. I hope you all are doing great. So today we are going to discuss abstractions from precipitation. Okay, we are going to discuss all the losses from precipitation. So this is your lecture number 11. I hope you have understood the entire concept of. See, we have discussed the basic introduction of hydrology. I hope you remember what is water cycle, what is water budget, all the basics things we have discussed. And I told you about the water budget equation. I told you that precipitation minus losses is none other than runoff. Okay, precipitation minus losses is runoff. Okay, so in the second chapter we have discussed precipitation, and today we are going to talk of losses. Okay, many losses we will discuss. We will discuss how many losses generally takes place, but we will discuss them one by one. So basically, we'll start with evaporation. I hope you all remember precipitation chapter. Okay, sir. Understood clearly now. So, firstly, we are going to discuss the loss which is known as your evaporation. Okay, evaporation. So, basically, in today's class, we are going to discuss evaporation and how to measure it. Okay, basically, evaporation and methods of evaporation, how to measure it, we are going to discuss that today. And secondly, we are going see. But before starting, let me tell you. Before starting, let me tell you. See, how many losses are there? Kindly comment in the comment box. How many types of losses are there? First, we will discuss and classify all the different kind of losses or abstractions which are taking place from precipitation. After that, we will discuss them one by one. Okay. See, in all the different if we will talk of different losses of precipitation, we will discuss. Basically, in each and every loss, let us say we are talking of evaporation, let us say we are talking of evapotranspiration, like this. So in all these, we are going to discuss first the factors. See, basically first we'll discuss what is the basic definition that you already know. Then we are going to discuss the factors which will affect evapotranspiration. Then we'll discuss how to measure it. Okay, then we'll discuss how to measure that loss. Okay, so basically in this chapter you need to understand. So can you guess how many uh, can you guess how many losses are there? How many losses are there? Just kindly comment, everyone. Yes, Vishal, absolutely correct. Evaporation, transpiration, infiltration, depression storage, Varga, all these are the losses. Very good. Great answer. Great. So we will discuss them one by one. I will write all these terms here one by one. So great answer by Vishal. Now, you need to understand in this chapter, we have basically five losses. Okay. Five losses are basically classified. The very first one is evaporation. Okay, the very first one is evaporation. Perfect. After your precipitation takes place, evaporation is there. Okay, then the second kind of loss is transpiration. The second kind of loss is transpiration. Okay, transpiration is the second kind of loss. Then the third kind of loss is infiltration. Third kind of loss is infiltration. So firstly we have evapotranspiration, transpiration, infiltration. Then at last we have depression storage and interception. Okay, depression storage and interception. In this chapter basically we'll deal with all these five kind of losses. So I have one question for you all. I have one question for you all. Can you guess out of these five which is the major one? Okay, see, you all know that, let us say this will be in some quantity, let us say 100 meter cube, this will be 1 meter cube, like this. Everyone will have different volumes. Okay, you all know that losses will take place, but obviously in different volumes. Yes or no? So can you guess which will be having the highest volume? Which will have the highest volume here? Can you guess? Kindly tell me. Try to tell me which will have the highest volume here. Just try to guess it. Let me see if you are able to connect. Good evening. You are unable to find it in the app itself. Okay, no problem. If it is not there, simply go to my Telegram channel. You all know my Telegram channel is Chetan Sir Official. Go there and in the files you will find the notes easily. Okay. Okay, Vishal. Yes, great Manjusha. Perfect answer. The I asked you one question that which will be in highest quantity. Obviously, infiltration is will be in the highest quantity. Yes, perfect. Great answer. Perfectly answered. So evaporation is denoted by E, transpiration is denoted by T, infiltration will be denoted by I or simply IF. Depression storage will be denoted by DS, and interception will be denoted by IL. Okay. So I already told you that let us say this is your land mass. We have certain depression here. This is your land mass. I told you after rainfall, whatever losses takes place, see some water will be filled in these depressions. Okay, some water will be filled in these depressions, and after these depressions are filled up, after that only you will see runoff is there. Okay, after that only you will see runoff is there. So basically, sir, you are simply saying that precipitation happened. After precipitation, all the losses occurred. Okay, all these five losses. See, these five are the major losses, but if you want to understand which is the most important loss or which will be in maximum bulk, that is infiltration. Okay, so these are major losses, and out of this, which is the highest one, that is infiltration. After these losses, runoff will take place. After these losses, sir, simply runoff will take place. Okay, so this I have already told you. I hope this thing is very, very clear to you. Now we'll be discussing one by one all the different kind of losses, what are the factors governing them, how we measure it. Okay, this is the ultimate aim of our chapter. Okay, so now firstly we are going to discuss your evapotranspiration. Firstly we are going to discuss evaporation. I hope you all know what evaporation is. Evaporation is simply what? Conversion of liquid state into gas state. Very simple. Okay. So evaporation is simply, see, obviously we are not going to write the definition here. Firstly, we will discuss what are the factors that will govern evaporation. Okay. Can you tell me what are the factors that will govern evaporation? Can you tell me? So we have many factors which we are going to discuss one by one. Perfect. Perfect. Now, these are all the factors which will be governing evaporation. The very first one is atmospheric pressure. So can you tell me if atmospheric pressure will increase, what will be the effect on rate of evaporation? Can you guess? Try to guess. See, you have to answer it, then only you will be able to understand it very clearly. Great, Vishal. Yes, perfect. Yes, you are saying it depends on temperature, it depends on humidity. Yes, many factors are there, but first tell me the significance of atmospheric pressure here. You are saying, everyone try to comment, see, if atmospheric pressure will increase, see, everyone try to comment, if atmospheric pressure will increase, then what will happen to rate of evaporation? Can you guess? You all are saying, tell me, will it increase or decrease? Rate of evaporation will increase or decrease? See, what is the meaning of, see, let us try to understand it beautifully. See, let us say we have a beaker here in which we have water. Okay. Okay, sir, no problem. Now, evaporation means, see, these water molecules which are present at the surface, will try to escape from the surface. Okay, they will try to get apart and they will get converted into molecules. And I hope this is very, very clear to you. Liquid phase will convert into gaseous state and they will escape. Okay, from here. Now, tell me, if atmospheric pressure from above, you know what atmospheric pressure is? Atmospheric pressure is the weight of all the gases which are present above us. Okay, I'm standing here and you all know we have a air column above us and it will have a weight. Weight, when it will be divided by area, will give you pressure. Yes or no? So I have a air column above me, simple, and that weight when divided by the area will give me the pressure. So atmospheric pressure simply means the weight of air above us. Yes or no? So tell me, if weight of air above us will increase, tell me, if this weight is increasing, if this atmospheric pressure is increasing, will the uh, molecules of water escape easily? Tell me. So you are saying, wait a second, Sushil, don't worry. Great logic. First, tell me this one. Atmospheric pressure. Now, if atmospheric pressure is increasing, if the weight of the air is increasing above us, then obviously these molecules will not be, you can say, will not be able to escape the surface easily. Okay, it is not easy for them because the weight is increasing. More the weight of the air, the molecules will find it, the water molecules will find it more tough to escape. Yes or no? So I can simply say that when atmospheric pressure increases, evaporation will go down. Yes or no? So I will say, as atmospheric pressure increases, rate of evaporation goes down. Okay, rate of evaporation goes down. So this is a simple logic, and reverse is the, and vice versa is also true. Okay, and vice versa, which means that when you will go at higher altitudes, such as you go to hill stations or hilly regions, there what you will observe that since when we climb the mountains, the atmospheric pressure is less because the weight of the air column will reduce above us. Okay, so when I will go to higher altitudes, or you can say mountainous or hill regions, there, sir, atmospheric pressure goes down. Since atmospheric pressure goes down, tell me, evaporation will be higher or lower? Everyone kindly comment. When we will go to mountainous or regions at higher altitudes, atmospheric pressure will decrease. So their evaporation will, tell me, their evaporation will what? Evaporation will decrease or increase? Everyone kindly comment, everyone. Try to comment, everyone. Try to guess the answer. It's very important. Try to guess the answer. Yes, it will decrease. Perfect. No, it will increase. When atmospheric pressure will decrease, evaporation will increase. Okay, so vice versa is the case. When atmospheric pressure is more the pressure, more the weight of air is there, more the weight of air, less is the evaporation. Less is the weight of air, less is the weight of air, higher is the evaporation. So reverse is the case. So in mountainous regions, since atmospheric pressure decreases, evaporation will increase. Okay, evaporation will increase there. Okay, I hope this is clear to you. Now, I hope the first factor is very, very clear to you. Now we'll move on to the second factor. Okay, now we'll move on to the second factor. We will discuss factors which are affecting your evaporation. Second factor is vapor pressure. This you can easily guess. Tell me, if there is more vapors, if there are more vapors or more humidity in the atmosphere, if there is more humidity, okay, more moisture in the surroundings, in the environment, then tell me, evaporation will be more or less? Guess it. Tell me. You all know that when we have drier atmosphere, then clothes gets drier faster. Okay, the clothes which we spread in the sunlight, you all know that they dry faster when we have a drier atmosphere. Yes or no? But when we have more humidity, then obviously the rate of drying, the rate of evaporation decreases. Yes or no? Yes or no? Perfect. Perfect. You all are guessing it correctly. When we have more humidity in the atmosphere, in the environment, then evaporation will be less. Yes, perfect. So I will write, when vapor pressure will increase, more moisture, more humidity is there, then obviously the rate of evaporation will go down. Rate of evaporation will go down. But drier the atmosphere, if moisture content, if humidity is less in the atmosphere, then obviously in that case, sir, evaporation will be more. Okay, I told you about one thing. I told you that rate of evaporation is proportional to saturation vapor pressure, EW, minus actual vapor pressure. See, this is the saturation vapor pressure. This is the highest amount of moisture that can be held by the atmosphere. Okay, and EA is actual vapor pressure. See, more the difference, this means that atmosphere has more capacity to hold moisture. So this was saturation deficit. I hope you remember this is saturation deficit. So more the saturation deficit, more will be the rate of evaporation. And if saturation deficit, or you can say moisture content, okay, if saturation deficit is low or moisture content is high, then in that case evaporation will be less. So higher the saturation deficit, higher will be the rate of evaporation. This is known as your Dalton's law. Okay, this is simply your Dalton's law. But basically, sir, you can simply say that more moisture, less evaporation, less moisture, drier the atmosphere, more is the evaporation. Okay, and vice versa is also true. So I hope this thing is very, very clear to you. Simple. Dalton's law is Dalton's law is simply higher the saturation deficit, higher is the rate of evaporation. Okay, perfect. Sushil is saying in mountain region evaporation also depend on temperature also as increase in altitude. Yes, dear, yes. It depends on that. But if we are assuming that temperature is constant, okay, at both the altitudes, if we are assuming that temperature is constant, see, whenever we are comparing one thing, if we are checking the effect of one parameter, then obviously second parameter we have to keep constant. Yes or no, Sushil? This you have to understand. Yes, perfect. Since I am considering one factor here, you need to understand we have to focus on one factor only. We are not going to discuss about the second factor. Okay, temperature, you are very correct about temperature here. When temperature will increase, then evaporation will increase. That is for sure. Okay, this is true. When temperature, Sushil is saying when temperature will decrease, rate of evaporation will go down, and when temperature will increase, see obviously more temperature is there, more will be the kinetic energy. You all know that whenever we have higher temperature, the molecules are more vibrant, they get more energy. Yes or no? They will be more in motion, and when they are in motion, obviously they have more skipping tendency, and they will easily skip the surface. So higher is the temperature, higher is the energy, and rate of evaporation will increase. Higher is the temperature, higher is the temperature, more is the evaporation. So sir, we can see here that temperature and rate of evaporation is proportional, but in the first two cases, rate of evaporation is inversely related to atmospheric pressure and vapor pressure. More the pressure of atmosphere, more is the vapor pressure, then evaporation will go down. Okay, I hope this thing is very, very clear to you. Now we'll move on to the third factor. So tell me if this thing is clear to you. Tell me till here all the points are clear to you. I hope these are clear. Now tell me about the quality of water. Can you guess if we have poor quality of water? Poor quality means impurities are there. Okay, see, we have two kinds of water basically. First is pure and second is impure. Sir, in pure water, sir, purely it will contain water molecules, nothing else will be there. It will contain no impurities. Yes or no? But in impure water, sir, what will be there? Sir, in impure water, I can see that dissolved salts, impurities will be there. Yes or no? So can you tell me if poor quality, or if we have more dissolved solids, or if we have more amount of impurities, then rate of evaporation will increase or decrease? Just try to guess it. Just try to guess it. I will tell you the answer. Try to guess. Try to guess. If we have poor quality of water with more dissolved solids, with more amount of, you can say, impurities, then evaporation will decrease or increase? Just try to guess. I will tell you the answer. Perfect, Sushil. You have given the correct answer here. Great. Perfect. Yes. Whenever we have, yes, if water quality will decrease, this is very, very true. When water quality will decrease, okay, we will have more impurities. We will have more impurities, or you can say dissolved solids. Yes, perfect. If we have more impurities, then poor quality of water will be there. When quality goes down, impurities increases. Now, sir, whenever impurity increase, wait a second, let me draw the diagram here. So let us say this is a beaker. Sir, earlier when water was pure, all the molecules at the surface were of water only. But now, sir, some molecules will be replaced by impurities. Okay, now some molecules will be of impurities. Why, sir? Because we have more dissolved solids. Okay, now you all know that at the surface, you should understand this thing that impurities or salts will not evaporate, only water evaporates. Now at the surface, you have less water. Initially, when water was pure, you have more water on the surface. Surface area was more. Yes or no? At the surface, we have more water. Yes or no? Exposed water that can evaporate. Now we have less exposed water. Surface area has gone down, so obviously less exposed water is there. So obviously evaporation will go down because some water molecules are replaced by impurities or dissolved salts. Yes or no? So what I'm going to write here is that quality of water, when it will decrease, it will increase impurities or dissolved salts. Hence, this implies that surface area of exposed water, as Sushil is saying, of water goes down, and hence rate of evaporation also, and hence rate of evaporation also decreases. So more the impurities, less is the evaporation. And you can say, if water is more pure, if it is pure, then obviously evaporation will be higher. Okay, so it's very simple to understand. I hope this is very clear to you. Now tell me the fourth factor. I hope this logic is very clear to you. Perfect, great answer. Now we'll move on to the next factor, which is our wind velocity. So wind velocity, if we'll talk of, tell me, if we have more wind velocity, tell me, if we have more wind velocity, then what will happen? Sir, if we have more wind velocity, then what will happen, sir? We have noticed this fact, we have witnessed this fact, that whenever we have more windy conditions, then our clothes dry faster. Have you seen this thing? Have you witnessed it? You must have observed that whenever wind is there, okay, you will see that your clothes, okay, dry faster. Why? See, there is a reason to it. Basically, we can write here that wind velocity, when it will increase, whenever wind velocity increases, my rate of evaporation, increases, that is for sure. But why, sir? The thing is, why this is happening? Okay, the thing is, sir, why this thing is happening? So, in order to understand this wind velocity concept, concept, see, we need to understand one thing. Let us assume we have we should make one lake here. Okay, let us assume this is a shallow kind of lake. Okay, in lake, you all know, we have certain depth of water stored, that is still water. Okay, let us assume this is your lake. Okay, sir. Now, one thing is for sure, above lake or in the vicinity of lake, you will have humidity. Okay, you all know that the surface of lake is very high, and obviously water will continuously get evaporated from here. So what you will see that above your lake surface, we have huge amount of humidity. Yes or no? This is humidity, which I am representing with simple dots. Okay, this is your humidity, and this humidity is nothing but the water vapor which has evaporated from your lake or the water body. Yes or no? Now tell me, yes, now tell me one thing, that when you have to understand beautifully, when wind will blow from this area to, see, I am going to draw one graph here, with the help of which you will be able to understand it easily. How should I draw it? Space is less, but still I will try to draw it here. Okay, we'll draw here now. Okay, so you can see that humidity is more. Okay, you can see that humidity is more just above the water body. Now when wind will blow in this direction, tell me, obviously the moisture or the humidity which has been stored here will move away. Yes or no, sir? Initially saturation deficit is very low. Why? Because saturation evaporation and actual evaporation are same. The entire air atmosphere above the water body is saturated, so saturation deficit is very low. There is no deficit here of moisture, so obviously rate of evaporation will be less. But when wind will blow in this direction, this moisture will get cleared up, air will become dry, and when air will become dry, there will be more scope for the moisture to evaporate again. So simply, sir, you are saying, when wind will blow in this direction, sir, I can see this graph going up. In that case, sir, I will witness that evaporation will increase like this. Okay, evaporation will increase. When wind is blowing, in this direction, sir, I will note that saturation deficit also increases and evaporation also increases. So when I will draw this graph, I will draw it like this, that rate of evaporation increases. Yes or no? I hope this thing is very clear to you. But wind is blowing in this direction, so that this saturation above the lake or the humidity above the lake gets cleared up. So basic role of wind is, see, wind does not do anything. Basically, you can say the action of wind is to clear off the moisture which has accumulated in the vicinity of the water body. It has to clear it off. When it will get cleared, again moisture will get evaporated. When it will get cleared again by the wind, again moisture will get evaporated, like that. Okay, so this is the ultimate mechanism with the help of which you will be able to understand how evaporation increases. So ultimately, sir, I will say saturation deficit goes down and rate of evaporation increases. Okay, so this is it. I hope this is very, very clear to you. But sir, one thing is there. One thing is for sure that if we will draw this wind velocity and rate of evaporation graph. Okay, so you need to understand here. Let me draw one graph here. Here we have wind velocity. On the x-axis, we have wind velocity, and that too in kilometer per hour. Okay, try to understand. Listen very carefully. Listen very carefully. Here on the y-axis, we have rate of evaporation. On the y-axis, we have rate of evaporation. So you need to understand, as wind will increase, wind velocity will increase, rate of evaporation will get increasing, but up to a certain limit. See, you can see here that wind velocity is increasing, but after a certain period of time, after this velocity, sir, I can see that rate of evaporation has become constant. After a certain velocity, the rate of evaporation becomes constant. Why? You need to understand this. See, the wind velocity after which your rate of evaporation becomes constant is known as critical wind velocity. Okay, this velocity is known as, let me write it here, the velocity above which the velocity above which your rate of evaporation becomes constant is known as critical velocity. But the thing is, sir, why rate of evaporation is stagnant now? Okay, no matter what, no matter how fast the wind blows, but still the rate of evaporation will become constant. Why? See, you need to understand one thing. Let us say 20 km per hour wind is there and your cloth is drying in, let us say, 5 minutes. Now you have increased the speed from 20 to 40. Now your cloth is drying in just 2 minutes. Okay, you have spread out a cloth in the sun and windy conditions are also there, and your cloth is simply getting dry. Okay, so now again you have increased the speed. Now your cloth is drying in 1 minute. Again you have increased the speed of wind by 20 km per hour. Now the cloth is getting dry again in 1 minute. Again you have increased the speed of wind. Again it is taking 1 minute. Okay, so we can see that after certain velocity, sir, I can see that what I can see here is that, sir, rate of evaporation is not increasing. It is taking same time again and again for that same cloth. Why? The thing is, you all can understand this fact that no matter how speed the wind is, but obviously your cloth will not dry in 0 seconds. Obviously, it will take certain amount of time. Yes or no? You should appreciate this fact that your cloth will take certain amount of minimum time in order to get dry up. Okay, so it will take certain amount of time. Obviously, that's why you can see here that after this wind speed, no matter how fast the wind blows, but still it will take certain amount of time in order to clear off the moisture above the water body, above the cloth. Yes or no? It will take certain amount of minimum time. See, if wind is blowing faster, this moisture will get cleared up faster. Yes or no? This moisture will clear off in a quicker way. But you need to understand that no matter how fast the wind is, but obviously this clearing up process, or this moisture which is present in the vicinity of the water body, will take at least some amount of time. It will never be 0 second. Okay, yes or no? So I hope this thing is clear to you. So obviously it will take certain amount of time. That's why after a particular speed, you will see that evaporation will become constant. Okay, so this is the thing which you need to understand. So wind velocity is also done, quality of water is done, temperature is done. Now we'll discuss the last factor, which is shape and size of water body. Okay, I hope all these points and all these factors are very, very clear to you. Is this thing clear? Kindly comment yes in the comment box, then we'll proceed further. Okay, so tell me if all these points are very, very clear to you. Then we are going to discuss the shape and size of water body. See, one thing is for sure. Let me ask you one question. Let us consider two water bodies. Okay, let us consider two water bodies. Sir, one has more area, one has more surface area, and one has less surface area. So, can you guess which will have more evaporation? If all the other things, volume and everything, climatic conditions, temperature, everything is same, if all the other factors, if all the other factors are same, tell me which water body will have more evaporation. Will it be higher for more surface area, or will it be higher for lesser surface area? Can you guess it? Can you guess it? Sir, you are simply saying in order to compare them on the basis of surface area. So tell me, how surface area of the exposed surface will determine your evaporation? You are saying more surface, more evaporation. Yes. In quality of water, saline water. Okay. Yes, Vishal, I have already told you. Vishal has doubt one. Vishal has one doubt here. See, in quality of water, you have more dissolved solids, more salts basically. In place of dissolved solids, you can write salts also. Okay. If you have, wait a second, if you have more salts, if you have more salts, obviously the exposed surface area will go down because some water molecules will be replaced by salt particles, and that salt particles are non-volatile. They does not evaporate. They are not volatile. Yes or no? So you need to understand that more the dissolved salts, more the impurities, lesser will be the rate of evaporation. That's why saline water, oceanic water evaporates less as compared to your normal water. Okay. Okay, Vishal. I hope this thing is clear to you. Understood. Now, Sushil, you are correct here. You have said the higher the surface area, higher is the rate of evaporation. Okay, this is very simple. But one thing is for sure that other factors and other parameters we have made constant. Okay, understood. So this thing has to be very, very clear. I hope there is no issues in that. So surface area, more surface area, higher will be the rate of evaporation. Now we'll consider them on the depth of water body. Okay, see, I have written shape and size of, see, we are discussing the fifth point, shape and size of water body. Now you need to understand we have two kind of water bodies. One water body is shallow and the other one is deep. Okay, we have two kinds of water body. You need to understand one thing here. So basically, sir, you are saying we have shallow water body and we have deep water body. Okay, so let me try to make it here. Yes, we have shallow water body. Shallow water body is simply water body which is not having too much of depth. Okay, and in comparison to this shallow water body, we have, and in comparison to this shallow water body, we have deeper water body, such as a deep lake or any kind of sea or ocean like that. So deeper water bodies obviously are very, very deep. Now, okay, so this is a shallow water body. This is a deeper water body. First, let us consider shallow water body. I am asking you one question. Listen very carefully and then answer it. Okay, so I hope you are ready for the question. Question is very simple. Just consider shallow water body. Don't consider this one right now. Now think of a shallow water body. Let us say we have a lake which is only 1 meter deep, not very deep. Okay, it is shallow. Now tell me, we have basically two seasons, summer and winter. You all know we have summer season and we have winter season. Can you guess in which season we will have more rate of evaporation? Can you guess in which season more rate of evaporation is there? Just try to guess it in shallow water body. I am seeing your answers. You are saying in pond more evaporation, but in streams less evaporation. Okay. Tell me in shallow evaporation, in shallow, sorry, shallow water bodies. Tell me, in shallow water body, evaporation is more in summer season. Okay. Yes, perfect answer, Sushil. Why? See, there is a reason to it. Reason is not so important, but the result is important for us. Okay, sir. If we'll consider them on the basis of evaporation, if we consider them on the basis of evaporation, then sir, obviously in summer season, sir, temperature of, see, the temperature of this water is important. If the temperature of this water is higher, if the temperature of water is higher, then evaporation will be more. See, you need to understand one thing. We have two temperatures. We have temperature of atmosphere or the air which is surrounding this water body, and secondly is the temperature of water. We have temperature of air and we have temperature of water. Temperature of water is more important. Temperature of water is more important. Higher the temperature of this water body, higher will be the evaporation. This you need to understand. Okay, this is the main concept here. This is the main concept. That's why in summer season, what happens in summer season, the temperature of this water increases tremendously, and because of this, you will see why the this shallow water body increases temperature. Why? Because volume of water is less. Since volume of water is less, it will absorb huge amount of heat energy and it will get heated up. And once it gets heated up, it will evaporate more. But in winters, sir, in winters, I will witness, or I should appreciate the fact that this entire water body will not have that much of temperature. Okay, in the winters, obviously the average temperature of this water body will be lower. That's why evaporation will be less. Yes or no? That's why evaporation will be less. Yes or no? Tell me. Perfect. Perfect. Now, what happens in deep water body? Sir, reverse is the case. Sir, in deep water body, in winters we have more evaporation as compared to summer. Okay, since deep water bodies are very deep, volume of water is also very high. So in summers, you will see that this amount of heat is not going into the water body. You will see that in summers, the water below the surface is very cold. In summers, you will see this. But in winters also water is very cold. In summers also water is cold. But in winters, what happens? In winters, basically we have layer of ice at the top. Let us say we are in some cold country, it was at 0 degree Celsius, but the lower water will be at 4 degree Celsius and it will be warm. It is warmer than the surface. Okay, even the outside temperature is going in 0 degrees or it is going in minus, no matter what, but still your below at temperature is 4 degrees Celsius, still water is warmer as compared to the outside temperature. That's why evaporation does not that's why evaporation takes place higher in winters as compared to your summers. Okay, so we have warmer water in winter season. All the water is at 4 degrees Celsius. So we have more evaporation as compared to summer. Okay, so this you need to remember. So opposite is the case as compared to shallow. Deeper water bodies, we have more evaporation in winters. Okay, the difference is not much, but yes, if someone asks you like in winters where rate of evaporation more, so you will say it is more in, yes, yes, Vishal, great. You have observed it. See, whenever deep water body is there in summers, that water body, you all know that water has higher specific heat capacity. It absorbs too much of heat in order to increase its temperature by 1 degree Celsius. That's why it is colder. Okay, so we are done with all the factors which basically affects your evaporation. So I hope all these factors are very clear to you. These are very simple. If some theoretical facts are there, one liner questions are there, so I hope you can easily solve them and you can understand what evaporation is. Okay, we are basically dealing with evaporation only right now. Now we'll move on to the methods with the help of which we will measure evaporation. See, for measurement of evaporation, basically we have three methods. Okay, for measurement of evaporation, we have three methods basically. The first is the first is the first is evaporimeters. First is the evaporimeter. Obviously, evaporimeter is a kind of meter which measures evaporation. Okay, simple thing. We'll discuss evaporimeters right away, but let us write down all the three methods first. So basically we have certain evaporimeters which measures evaporation. Secondly we have um, secondly we have your empirical equations. Secondly, we have empirical equations for evaporation. Thirdly, we have some analytical methods. Okay, thirdly, we have some analytical methods for measurement of evaporation. Now, in evaporometers, we will discuss Indian standard method. Okay, we will discuss US one, but we'll discuss that, no worries. Empirical equations are certain formulas. Okay, empirical equations are certain formulas with the help of which we'll find evaporation directly. Basically, one formula which is important is your Mayer's formula. Only this one is important. Okay, see, basically we have many scientists who came up with different formulas, but Mayer's and Rover's formulas were dominant, and the formula which is little bit important for our syllabus is Mayer's formula. There is no need to remember Rover's formula. Rover's formula is very tough and it's very lengthy, so there is no need to remember it. Okay, and then in the analytical method, see, in the analytical method, analysis is done. Okay, we will do the analysis of a water body on the basis of water budget, or let us say energy balance, like this. Okay, so in analytical methods, basically we have three methods. The first is water budget method. The first is water budget method. Okay, with the help of this water budget method, we will simply find evaporation in a water body. Second method is energy balance. Second method is energy balance method. Okay, second method is energy balance. Second method is energy balance method, and third one is mass transfer approach. Okay, third one is mass transfer approach, or simply method. Obviously, out of these three, the third one is the best one. Okay, if we are finding evaporation with the help of analytical methods, the best one, or the method on which we can rely the most, or the most reliable method will be, out of these three, will be mass transfer method. Okay, let me write down the order of reliability here. If we want to write down the order of reliability, like which method is most accurate, okay, which method is most accurate here, if we want to note it down, I will say that water budget method is the least reliable. Okay, it is the simple one, it is the least you can say accurate, but most simple one. Okay, since it is simple, it is very popular. Water budget is least reliable. It will not give you the best answers. Okay, it will not give you the best answers. Okay, it is least you can say accurate. Then energy balance is even better. Energy balance is even better method as compared to water budget. Then mass transfer is even better. Okay, mass transfer method is the best method. Mass transfer method will be the best one, but that we don't have to study, because since it's a part of advanced hydrology, it's little tough. Okay, yes, perfect. Now we'll move ahead. I hope this concept is clear to you. Now one by one we'll discuss all the different types of methods. Okay, see, if someone asks me, like, out of these three methods, which is the most important, so I will say the first evaporimeter thing is very important. Okay, you should remember the evaporimeter concept. Okay, so now we'll move ahead and discuss all the different kind of evaporimeters. So basically we have an image here. Okay, and in this image you can see we have a evaporimeter here. We have a pan. Basically this is your evaporimeter. Okay, and it is simply measuring evaporation. So you can see one table is here. And in this we have mentioned different kind of evaporimeters. Basically pan, see, this is a kind of pan. So pan is simply your you can say a kind of instrument in which water is filled up to a certain level, and after a day or so we measure how much depth of water has depleted there. Let us say 5 mm. So 5 is the depth of evaporation. Okay, like this. So basically we have different kind of pans, and we measure evaporation with the help of these evaporimeters. Okay, but four are there, only two are important. First two are important. Only these two are important for us. Okay, so wait a second. Let me drink water. Yes. So what I'm saying is only first two are important for us. Okay, only first two are important. The very first one is used in USA. Okay, only wait, let me tell you. Let me tell you with the help of an example. See, this evaporimeter thing is very, very important. So, sir, you are saying that class A land pan. See, this pan is basically was invented in USA. Okay, their meteorological department uses class A land pan. It is also known as US pan. Okay, sir, clear. So this US pan is made out of GI sheet, galvanized iron sheet. I hope you know what galvanized iron is. When iron is coated with zinc, okay, whenever iron is coated with zinc, so that rusting does not take place, that is known as your GI sheet. So class A pan is made out of GI sheet. Understood, sir. Then we have ISI pan, Indian Standard pan, which is very very similar to class A US pan, which is very similar to the first one, but some modifications are there. Okay, Indian scientists have improved that one and have come up with the modified class A pan. So you can see average value of pan coefficient is written in each in front of each evaporimeter, in front of each pan. So these values are important. Colorado sunken pan, USGS geological survey floating pan, these are not so important. Okay, floating pan is, see, let me tell you, see, these class A land pan and near stand pan are installed like this. Okay, we have a wooden base, and this wooden base you can see is little away from the ground, so that air can pass through it, so that air from the bottom can pass through it. So the first two are installed somewhat in this fashion. Okay, this is your GI sheet. You can see this is made up of GI sheet. Diameter is 1210 mm, like this. Height is somewhere around 250 mm. Okay, so height, dimensions, see, different dimensions are there. There is no need to remember that, not so important. Okay, but the thing is, the first two the first two are installed above the land. Okay, the first two are kept just above the ground. But the third one, as the name tells you, Colorado sunken pan. The third one, as the name tells you, Colorado sunken pan. See, why the name sunken is there? Because that pan is somewhat sunk into the ground. Okay, that pan is going into the ground. Yes or no? See, that pan is sunk into the ground. That's why its name is Colorado sunken. So this is below ground. This is installed above ground. And USGS floating pan is made to float on water body. Okay, let us say we have a huge lake, and on that huge lake we have a floating pan. So that is your USGS floating pan. Okay, we are not going to discuss floating pan, sunken pan, these are not so important, but class A land pan are important for us, so we'll discuss them only. Okay, so I hope this is clear to you. We will solve one question also. Okay, now one formula is very very important here. See, one or two points let us write down. Class A land pan, if we talk of class A land pan, it is made up of GI sheet. Let me write here. Let me write here that class A land pan, class A land pan is, or simply let me write in the bracket US pan. Okay, this is a pan which is made in US. So class A land pan is made of GI sheet, is made of galvanized iron sheet. Okay, its diameter is 1210. Okay, diameter of this pan is 1210 mm, and depth, height, simply height of this pan is 255 mm. Okay. So Indian pan is also somewhat similar, but they have changed the metal. Okay. They have changed the metal, little diameter they have altered. Okay, but it is very, very similar to your USA pan. Okay, remember the pan coefficient here. This also will uh, discuss right now. So this is class 11 pan. Then we have Indian standard pan, IS pan. Okay, ISI pan is also known as modified. ISI pan is also known as modified class A. Is also known as modified class A. So it is made up of, ISI pan is made up of 0.9 mm copper sheet. Okay, so basically it is made up of copper. ISI Indian standard pan is made up of copper. Its diameter is similar to the its diameter is similar to that of class A land pan, 1220. It is 1210. This is 1210, so this is 1220. Oh, okay, little diameter they have increased. Height is similar. Height is also similar, 255. Only thing is they have changed the metal. Okay, here you can see iron is there. Here galvanized iron GI sheet is there, and in the Indian standard one we have copper. Okay, understood, sir, clearly. Now we have one thing here, pan coefficient. Okay, see what is this pan coefficient, sir? What is this pan coefficient? You need to understand one thing. If you want to find uh, evaporation of any water body, let us say we have any kind of water body, let us say we have a lake, and if you want to find evaporation of that water body, then first you will install pan in the vicinity of that water body. Let us say we have a lake. Okay, so in the vicinity of that lake you will install one pan. Okay, you will install one pan there. Okay, and how you will find the actual water body evaporation? If you want to find actual water body evaporation, or let us say we have a lake, if you want to find actual lake evaporation, if you want to find actual lake evaporation, what you have to do, you simply have to do what? If you want to find actual lake evaporation, what you have to do, you have to multiply pan evaporation. See, that pan is also installed in the vicinity or in the nearby area of that lake. That pan evaporation has to be multiplied by pan coefficient. Okay, cp is what pan coefficient. Okay, so pan evaporation, when it will be multiplied by pan coefficient, we will get actual lake evaporation. One thing is for sure, see, remember these pan coefficients, this is 0.7, this is 0.8, this is 0.78. Okay, 7 from here, 8 from here, 7, 8, but this is not important. Only remember for US one and remember for Indian one. Okay, I hope pan coefficients are clear to you. Is this thing clear? Tell me, pan coefficient thing is clear to you? Tell me, everyone. Yes. Yes, perfect. So it is clear to you. Now we'll solve one question. Acha, one question is there. I want to ask one question. Can you tell me where evaporation is more? Is evaporation more in pan or in lake? Just tell me where we will have more evaporation. If we want to write down the order of evaporation, which will have more evaporation, lake or pan? Just try to guess. Just try to guess. After this, we will solve one question. Okay, we have a question which we have to solve. So this is a question. Just guess. You are saying lake due to more surface area. No, no, no. We are not talking of more surface area. See, tell me, Sushil, if both have same surface area, then where more evaporation will be there? All the things are constant. All the things are same. All the things, wind condition, temperature, surface area, all are same. If you have a lake and if you have a pan, both have same surface area, then where more evaporation will be there? Can you guess now? Now try to guess it. No, listen very carefully. I will give you the concept. So first let us read this question. Okay, First, let us try to read this question, then I will give you the explanation where we have more evaporation. Is it more in lake or it is more in pans? Okay, so it is saying a standard ISI pan is installed at the banks of surface reservoir. I hope you all know what reservoir is. Okay, reservoir is a very big pond. Reservoir is a huge pond in which huge amount of water has been collected. Okay, for the further use. Let us say we have to use it for irrigation, or let us say we have to produce hydropower from it. Okay, so I hope you all know what reservoir is. Reservoir is basically uh, made by constructing a dam across a river. Okay, when you will construct a dam across a river, so behind that dam huge amount of water will get stored up. Okay, so let us say this is your, let us say this is your reservoir. Okay, let us say this is your reservoir. Huge amount of water has been stored behind this dam. Okay, let us say this is your dam. Okay, so we have a huge reservoir, and in this huge amount of volume water has been stored. Understood, sir, clearly? They are saying the surface area on a day was 100 hectare. Surface area of this reservoir, surface area of this reservoir was 100 hectares. No problem, sir. Now they are saying a pan was installed near this lake or reservoir. Okay, let us draw a pan here. Okay, let us draw a pan here. So, sir, for pan we have a wooden base. First we have a wooden base, and on that wooden base, sir, a pan is installed. Let us say this is the pan. Okay, this is the pan, and since they have said Indian standard pan, let us say we have a wooden base, and on that wooden base we have a pan installed. Okay, the diameter of this pan will be 1220, height is 250, like that. Okay, basic. Now they are saying the recorded evaporation loss from the pan on that day is 4 centimeter, which means, listen very carefully, the depth of water which has been depleted in a single day is how much? 4 centimeter here. Okay, in pan, how much depth of water has depleted? 4 centimeter. In pan, how much depth of water has depleted? I will write, some things are given to me in the question. Okay, pan evaporation is given to me as 4 centimeters. Pan evaporation is given to me as 4 centimeter. Now, what will be the evaporation loss from the reservoir? Okay, so we have to find the how much water will get lost from this reservoir, from this lake, in single day. Okay, so how I will find? Yes, perfect. Yes, Sushil, don't worry. Sushil is saying unable to clarify this question. See, don't be worried about this question. It's a simple question. We have a reservoir. Okay, we have a lake here. Okay, we have made a dam. You know what dam is. Behind dam, huge amount of water is stored. We have a water, huge amount of water, and the surface area of this lake or this reservoir is 100 hectare. That is also given to you. Okay, let me write here. Area of this reservoir is 100 hectare, and in the vicinity of this lake only we have installed a pan, and in that pan, in a single day, 4 centimeter water has been lost. Now, how much water will be lost in the lake? Okay, so how much water will be lost in the lake will be dependent. See, we have a formula here. We will use this formula. Actual lake evaporation is given by, we will simply use this formula. Okay, actual lake evaporation. Okay, lake is having less evaporation, so we have to multiply pan evaporation by Cp. We have to multiply pan evaporation by Cp. So simply, since this is Indian standard pan, and tell me what will be the Cp for Indian standard pan. Tell me what will be the value of Cp for Indian standard pan. For Indian standard pan, it is 0.8. Yes or no? For Indian standard pan, it is 0.8. This you have to remember. Perfect. So what I will do, I will multiply pan evaporation by 0.8. Okay. What I will do here is, I will multiply pan evaporation, that is 4 centimeter, by 0.8. This means, now listen very carefully. Let us say we have water filled in this pan. Water which is depleted in a single day is 4 centimeter a year. Yes or no? But in lake, but in lake, the level of water which will get dropped is 3.2 centimeter. In lake, the level of evaporation is 3.2 centimeter, and here in this pan we have 4 centimeter evaporation. Is this thing clear? Tell me, is this thing clear? Sir, in lake 3.2 centimeter and in pan 4 centimeter. That means pan has more evaporation. Okay. If we talk of constant area, if both of them, let us assume if pan and lake both have same areas, then also pan will have more evaporation. Then also pan will have more evaporation. Okay. Sir, you are simply saying that pan will have more evaporation. Sir, why? Can you tell me, sir, why? Because pan is made out of metal. Yes or no? Metal, you need to understand, metal will perceive temperature. You can say it is more susceptible to temperature. It will perceive temperature in a better way. If it will perceive temperature better, then obviously temperature will increase immediately, and higher will be the rate of evaporation. Okay, but you all know that lake is not made out of metal. Okay, in lake we have surrounding, it is made out of soil. Yes or no? Lake surrounding is basically made out of soil, so there is difference between soil and metal. Soil will behave differently and metal will behave differently. Metal will give you more evaporation. Yes or no? Because it perceives temperature or heat quickly. So pan evaporation is more as compared to lake evaporation. After many observations, listen very carefully. After many observations with the help of this class A pan, they have come up to the conclusion that when you will multiply pan evaporation with the value 0.7, then you will get actual lake evaporation. That means lake evaporation is somewhere around 70% to that of pan evaporation, which is in the USA. Okay, US pan. You need to understand one thing here, that USA pan or class A land pan, it is placed on land, that's why land pan name is there. So class A land pan is having 70% evaporation as that of lake. Generally they are saying that they have conducted many experiments. Okay, USA, American Meteorological Department have conducted many experiments, and they are saying that the range of this evaporation, pan evaporation, pan coefficient, sorry, pan coefficient varies from zero point 0.6 to zero point 0.8. Sometimes it is 60%, sometimes it is 80%, but on an average the value is 70% to that of pan evaporation. Okay, lake evaporation is 70%. Lake evaporation is 70% of approximately of that pan evaporation. And similarly, that's why, see, now Indian people, what they did, Indian Meteorological Department, what they did, they tried to make this pan evaporation and lake evaporation even closer. Okay, they wanted that lake evaporation is more or less similar to pan evaporation. So what they did, they changed the metal. Okay, they changed the metal to copper. So because of that, you will see that now pan evaporation, that lake evaporation is now 80%. Lake evaporation is somewhat around 80%, and you can see the range 65 to 110%. Yes or no? So Indian pan is better. Why? Because lake evaporation is almost similar to pan evaporation. Yes or no? Lake evaporation is almost similar to pan evaporation. So lake evaporation will be similar to pan evaporation when the Cp is equal to 1. So where this Cp is highest, can you see where this Cp is highest? Cp is highest for Indian pan and floating pan. Floating pan basically floats on that lake. Okay, floating pan basically floats on that lake. That's why it will perceive better evaporation. Yes or no? So I hope this thing is very, very clear to you. Yes or no? So I hope this thing is very clear to you. Now if someone asks you, if someone asks you what is the order of evaporation, what is the order of evaporation if we talk of these three evaporimeters, if we talk of the first three evaporimeters, can you tell me where evaporation will be highest in these three? Evaporation will be highest in which of them? Can you guess? Can you guess where evaporation is highest and where it is lowest? Out of these first three, class A land pan, Indian stand pan, and Colorado sunken pan, can you guess which has the highest amount of evaporation and which has the lowest one? See, USA one, this class A land pan US one will have the least evaporation. Okay, sorry, it will have the highest evaporation. Okay, it will have the highest evaporation. How come? Sir, it is having the highest. Listen very carefully. I am seeing your comments. See, this class A land pan is having the highest evaporation. That's why you have to multiply it by 0.7 so that it becomes equal to lake. You all know, you all know that no matter what happens, but lake will have same evaporation every time. But in the vicinity, if you place one time, let us say you are placing class A land pan. Secondly, you are placing Indian stand pan. Third time, you are placing Colorado sunken pan. In all the cases, you will see that pan evaporation is different. But where it will be highest? Sir, it will be highest in case of class A land pan. Okay. Sir, class A land pan will witness highest amount of evaporation. Okay. See, the lower the pan coefficient, the higher is the evaporation. Secondly, we will have Colorado sunken. Secondly, we will have Colorado sunken pan. And in Indian one, evaporation will be almost similar to lake. In Indian one, it will be almost similar to lake, very, very less. Indian pan, ISI pan will give you the lowest evaporation, similar to that of lake. That's why it is the best one. Class A land pan, which is having CP as 0.7, this is having CP of 0.78, this is having CP of 0.8. We can clearly see that class A land pan, since it is giving you the highest evaporation, in order to make it equal to lake evaporation, listen very carefully. See, it is giving you the highest value. Okay, it is giving the highest value. So in order to make it equal to lake, you have to multiply it by 0.7, 70%. You have to reduce it. Since you want to reduce it, pan coefficient is least. Why pan coefficient is least here? Because evaporation is very, very high. Since evaporation is very, very high, that's why pan coefficient is very, very less. So that when you multiply it, the evaporation becomes equal to lake evaporation. Yes or no? Yes or no? Is this thing clear? But since Indian pan does not evaporate too much of water, already Indian pan gives you lesser evaporation, and that too equal to that of lake evaporation. That's why pan coefficient is near to 1, or you can say more. If you have Cp equal to 1, if you have Cp equal to 1, it means it has lower evaporation, and evaporation is so low that it is equal to lake itself. That's why Cp is equal to 1. So higher the Cp, more near to 1. If it is more near to unity, then I will say evaporation is less. And it is so less that it is equal to your lake evaporation. I hope this is clear to you. Okay. I'm repeating it. Just try to understand. Just to try to understand. Let me give you some example. With the help of that example, you'll understand. Okay. It's not that tough. So one thing is, see this metal, this GI sheet, basically you need to understand. See, class A land pan, Colorado sunken pan, both are made up of GI sheet. So they will easily evaporate. Just try to understand. Let us say we have to make lake evaporation 100 centimeter. This is lake evaporation. Okay. This is Colorado sunken pan. Let us say X pan evaporation. This is class A land pan. This is Colorado sunken pan. This is Indian standard pan. You multiply this by 0.7 to get 100. You multiply this by 0.78 to get 100. You multiply this by zero point 0.8 to get 100. Okay. No matter what you multiply by 0.7, 0.78, zero point 0.8, you will get 100. Lake evaporation will be same every time. But tell me which value will be highest here. If you will see, X will be highest. Since X is highest, you have to multiply it by least pan coefficient. Since X is highest, you have to multiply it by least pan coefficient so that lake evaporation is same. Because class A land pan gives you highest amount of evaporation, that's why you have to reduce it to the maximum level. That's why its pan coefficient is less. I hope now this is clear. Now, since Colorado sunken pan does not have that kind of evaporation, that's why its pan coefficient is more. And Indian sand pan, this is class A. This is class A, this is Indian pan. Okay, now for Indian pan you need to understand Indian pan. For Indian pan you need to understand we have very less evaporation, so less that you have to multiply it only by zero point 0.8. Okay, you have to only multiply it by zero point 0.8. It's a more, it's a bigger number. Okay, so since this number is big, since this pan coefficient is more, that means evaporation is less as compared to this one. Again you will obtain 100 centimeter. Okay, so I hope you have understood this thing. So simply, sir, you are saying pan coefficient, pan coefficient is inversely related to evaporation. Higher the evaporation in the pan, higher the evaporation in the pan, lower will be its pan coefficient. Higher the evaporation in the pan, lower will be its pan coefficient, so that when we multiply it we get the correct lake evaporation. Okay, we get the correct lake evaporation. If pan evaporation is less, if pan evaporation is less, then pan coefficient will be more. If pan evaporation is less, let us say pan evaporation is so less, pan evaporation is so less that it is equal to 100. Okay, pan evaporation is also equal to 100. So in that case Cp will be 1. Okay, the lowest amount of evaporation which can take place here is basically 100. In that case you will see that pan evaporation, lake evaporation both have become equal, and in that case Cp will be equal to 1. When Cp is 1, that means your pan is replicating the lake itself. Okay, so it's a simple kind of strategy. I hope this is very clear to you. Yes or no? Have you understood? But even if you haven't understood, there is no need to worry. Simply understand that Cp is inversely related to rate of evaporation. This you can write here. Okay, let me write it here, that amount of evaporation, amount of evaporation is inversely related to Cp. Okay, so since class A pan has lowest Cp, it means its evaporation is highest. Okay, since class A pan has lowest Cp, that means its evaporation is highest. Have you understood now? Tell me. Not so important, but still I have explained it to you. Okay, perfect. Now we'll move ahead. So Indian sand pan is the best one. Now in this case, it is saying actual lake evaporation is 3.2. Here in this pan, we have 4 centimeter evaporation. In lake, we have 3.2 centimeter evaporation. Now, if you want to find actual volume of water which has been evaporated, volume of water that is evaporated from this lake in a single day, in one day, they are saying volume of water that is evaporated from here is, that is evaporated in a day, will be what? Area into, area is 100 hectare. Hectare you all know. Where is 100 hectare? Yes, area is 100 hectare. Hectare is 10 power 4 meter square. You all know 100 hectare. Hectare is 10 power 4 meter square into depth. Depth is 3.2 centimeter. Depth is 3.2 centimeter. Convert this into meter. Okay, 100 will get cancelled. This will be 32000. 32,000 meter cube per day. Every day, how much volume of water is getting evaporated from here? 32,000 meter cube. Huge amount of volume. Okay, this is huge amount of volume. Perfect, Sushil. I hope this thing is clear to you. Now we'll move ahead. So I hope this concept is clear to you. This can be asked in your gate examination. So try to remember this evaporimeter thing. So I hope now the evaporimeter part is clear to you. Okay, evaporimeters are sometimes also known as atmometer. Now we'll discuss empirical equations, and in that we will discuss firstly the Mayer's formula. Okay, but before that we are going to discuss some recommendations of WMO. WMO stands for World Meteorological Organization. So according to WMO, some recommendations are there that minimum network of evaporimeter stations should be, see, arid means dry. Okay, arid means dry zone. So you all know that in dry areas we have more evaporation. In dry areas we have more evaporation, and in cold regions we will have less evaporation. So in arid zones we should have one station for every 30,000 kilometer square. For humid temperate climates, we should have one station in every 50,000 kilometer square, and in cold region we should have one station for every 1 lakh kilometer square. This is the basic recommendation. So I hope this thing is very, very clear to you. So this is the recommendation which you should remember. Not so important, but yes, it can be asked in your ESC engineering services preliminary examination. Now we'll move ahead and move on to empirical equation, Mayer's formula. Okay, now we have to discuss Mayer's formula. Where is Mayer's formula? Yes, this is your Mayer's formula. So what is Mayer's formula? It's very simple. Mayer's formula is given by EL. EL equals Km. Km is your Mayer constant. EW minus EA 1 plus U9 upon 16. This is your Mayer's formula. In this Mayer's formula, you will find lake evaporation. This is EL. EL is lake evaporation, which is found out in MR. So this is an empirical equation. So obviously, in what units we have to put, all these things are already mentioned. EL is lake evaporation. EL is lake evaporation. Okay, and it is in mm per day. Okay, what is Km? Sir, Km is Mayer's constant. Km is Mayer's constant. Km is Mayer's constant, and whose value is, see, its value is 0.36. Its value is 0.36 when water body is deep. Okay, for deep water bodies, and it is 0.5. It is 0.5 for shallow water bodies. Okay, for shallow water bodies, because in shallow water bodies you need to understand we have more evaporation, and since we have more evaporation, the value of Km, Mayer constant, will be more. Now, what is EW? EW is saturation vapor pressure. Saturation vapor pressure at the temperature where your evaporation is taking place. Saturation vapor pressure in mm of Hg at a given temperature. Then EA is actually, see, this saturation vapor pressure and actual vapor pressure we have already discussed in the starting of precipitation. I hope you remember it. EA is actual vapor pressure. EA is actual vapor pressure in mm of Hg. Now, what is 1? You all know 16. U9 is wind velocity. U9 is wind velocity at 9 meter above the ground. What is the meaning of 9 in the subscript here? Wind velocity at 9 meter above the ground. Wind velocity at 9 meter above the ground. And in order to find this velocity, and this is in kilometer per hour, in order to find this velocity, you have to use 1 by 7 power law. Okay. What is 1 by 7 power law? Let me explain it to you here. So 1 by 7 power law is simply 1 by 7th power law is nothing but it is simply, wait a second, 1 by 7th law, 1 by 7th power law is basically UH is proportional to H power 1 by 7. Velocity at any height is proportional to H power 1 by 7. This is constant. Simply put the value of H and get the value of velocity at that height. If you will put 1 meter, you will get velocity at 1 meter. If you will put 2 meter, you will get velocity at 2 meter. If you put 9 here, you will get velocity at 9 meter. Yes or no? Okay. So this is your Mayer's formula. This is your simple empirical formula. I hope this is very, very clear to you. Now we have one question. We'll discuss this question. We'll simply use Mayer's equation. We'll simply use Mayer's formula and try to solve this question. Okay. So sir, this question is saying a reservoir with a surface area of 250 hectares. We have a reservoir. Okay. We have a reservoir. You all know what reservoir is. Behind dam, You all know that behind dam we have a very big reservoir, okay, in which huge amount of water has been stored. Okay, I hope you all know what reservoir is. And the surface area of this reservoir is given to me as 250 hectares, and water temperature is 20 degrees Celsius. Okay, water temperature is 20 degrees Celsius. So I hope this thing is clear. Relative humidity is 40%. Wind velocity above. So let me write down all the things which are given to me. Area is 250 hectares. Relative humidity is 40%. See, what is the meaning of relative humidity? This simply relative humidity is what? Actual vapor pressure upon saturation vapor pressure. This is 40%. If we have saturation vapor pressure, we will multiply it by 40% in order to get how much vapor pressure or how much moisture is there at present in the atmosphere. At present, we have 40% moisture content, 40% vapor pressure as that of maximum value. Okay. So actual vapor pressure will be, this simply signifies that actual vapor pressure is 40% of saturation vapor pressure. Okay. Then wind velocity above 1 meter ground, U1, wind velocity above 1 meter ground is 16 kmph. This is given to me. Then saturation vapor pressure is, saturation vapor pressure EW is given to you as 17.54 mm of Hg. So if saturation vapor pressure is given to you can simply find out the actual vapor pressure. Simply it is 40%. 40% of saturation. Tell me how much we are getting here. Tell me how much we are getting here. 40%. So when you will solve 40%, you will get it as, when we will do 40%, we will get it as how much? Yes, we are getting it as 7.02. Yes, 7.02 mm of mercury. Okay, pressure you all know that it is measured in column of mercury. Estimate the average daily evaporation from lake using Mayer formula. And ISI pan measured weekly evaporation as 72 mm. Comment on the difference. So ISI pan has also measured the evaporation here, and Mayer formula has also measured the lake evaporation. So we'll see the difference, how much difference is there. But first, let us use Mayer's formula. But first, let us use Mayer's formula. Okay, sir, this is Mayer's formula. Okay, this is Mayer's formula. We have all the things here. Okay, but U9 is missing. We don't have U9 here. Okay, so sir, one thing you have told us. See, you told us UH is proportional to CH power 1 by 7. U1 is given to us U1. 1 means height is 1. When height is 1 meter, tell me what is, sorry. Yes, we will put 1 here. Height is 1. But we are interested in finding U9. We are interested in finding the velocity at 9 meters. So I will put 9 power 1 by 7. So this U1 thing is given to us. U1 is 16. Yes or no? U1 is 16. Okay. Yes, perfect. U1 is given to us as 16. Great. Perfect. So U1 is 16. I will write 16 here. I will write 16 here. See, from this equation, you have to find C, and from this C you have to put it here and find U9. Okay. So if you will divide them, if you will simply divide them, we will get the value of U9. So 16 upon U9, C and C will get cancelled. 1 upon 9 power 1 by 7. So from here we will get U9. From here we will get the velocity at 9 meter. Yes or no? Tell me how much velocity we are getting. Tell me how much velocity we are getting here. Tell me, just try to tell. Multiply it. U9 will be going here, and 16 multiplied by 9 power 1 by 7 will be, U9 will be equal to, I guess, 21.89 kmph. Yes or no? Are you getting this value? Perfect. Perfect, Sushil. Yes. Now we'll simply put the values. Okay. So if we want to find the lake evaporation in mm per day, so the value of km, see, we have reservoir here. Reservoir is already very deep. Reservoir has too much of water already. So the value of km which we will use, the value of km which we will use is 0.36. Why? Because it is deep water body already. Okay. So I will use 0.36 here. I will use 0.36 here. EW is 17.54. Actual vapor pressure is 7.02. Okay, 1 plus U9. U9 is 21.89 divided by 16. So how much lake evaporation we are getting here? Try to comment. Tell me how much evaporation we are getting here in per day. How much we are getting it? Use Mayer's formula and try to find the lake evaporation. The value which we are getting here is, yes, Sushil, perfect, 8.97. Great. We are getting it as 8.97. Perfect. So Mayer's formula is very, very clear to you. Now the second part of this question is saying that in an entire week, we have an Indian standard pan, and in that Indian standard pan, in entire week, we have 72 mm of evaporation. So how much will be the evaporation in one day? See, this evaporation is in one day. This evaporation is in single day. So tell me, uh, in a single day, how much will be the evaporation? Daily evaporation will be how much? Daily pan evaporation will be how much? Daily pan evaporation, sir, will be, it's simple, 72 by 7. Okay. 72 is weekly evaporation, so obviously you have to divide by 7. Perfect. Now tell me what will the lake evaporation? Tell me what will be the actual lake evaporation. Sir, it's very simple. We have to multiply this value. We have to multiply this daily value by pan coefficient. And for Indian standard pan, sir, I know for Indian standard pan, sir, we have, wait a second, the pan coefficient value is 0.8. Yes or no? 0.8. Perfect. For Indian standard pan, the value is 0.8. So wait a second. I will multiply this value 72 by 7 by 0.8. So tell me how much lake evaporation we are getting on a daily basis. Tell me how much is this value. Daily pan evaporation is 72 by 7. 72 by 7 multiplied by 72 by 7 multiplied by zero point 0.8. This is 8.23. Yes, 8.226. So we can round it off to 8.23. So now you can see that Indian standard pan is giving you 8.23 and Mayer's equation is giving you 8.97. Yes or no? Both are giving different answer, but yes, more or less they are same. Okay, see, we have different methods. From each and every method, you will get different answers. Okay, from each and every method, I told you today that we have different. Okay, I told you that we have different methods where yes, this slide. So we have evaporometers, we have empirical equations. See, all these methods, rover formula, Mayer formula, evaporometer, water budget, energy balance, mass transfer, all will give you different answers. But some are more accurate, some are less accurate. Okay, some methods will give you very closer value to practical values which are there in the field. Some methods will give you the exact values as that in the field. Yes or no? Are you able to understand this thing? So we are not going to predict here which is more correct or which is less correct, but we have understood that Mayer formula will give you different answer, Indian standard pan will give you different answer, classical land pan will give you different answer, water budget will give you different answer. Okay, I hope this thing is clear to you. But yes, some methods are more reliable on which we can trust more. I hope this thing is clear to you. So after this we have to discuss analytical methods, and analytical methods are not so important, only water budget we have to discuss. So shall we discuss it, or shall we discuss it tomorrow because time is over? Let us discuss. It's very simple. See, in water budget it's very simple. Let us imagine we have a lake. Okay, and in that lake, let us assume certain rainfall is there. Okay, let us say certain rainfall, precipitation P is there. Let us say some water has come inside. This is volume of water which is coming inside from surface. VIS means volume of surface inflow. Let us assume some water has come from ground itself. Okay, some water has come from ground itself, so it is VIG, volume of groundwater inflow. Let us say some water has run off from the surface, that is VOS, volume of surface outflow. Let us say some water has gone from ground, that is VOG, volume of groundwater outflow. See, some water can come from surface, some water can come from ground, some water can go from surface, some water can go from ground. Okay, what else can happen? Obviously some water will go away in the form of evaporation. Yes or no? Like this you can write on the different phases. There is no, just I am trying to give you an example. Now if you will apply water budget, okay, so this method is simple. See, this method is simple but least accurate. This method is simple but least reliable. But sir, how I will find evaporation with the help of this equation? Simply you have to apply water budget. You all know that inflow minus outflow equals delta S. So in this equation, what is inflow? Inflow is precipitation. Precipitation is coming. VIS is coming. VIG is coming. Okay. All the terms which are coming, you have to write them and group them together. All the terms which are going, okay, surface water outflow, groundwater outflow, transpiration can be there. Okay, let us say some plants are there and transpiration is also there, so you will write transpiration also. And then we have uh, transpiration will be denoted by T only, and we have evaporation from the lake. This will be equal to delta S. So this is your equation. If you have the values of all the other things, you can simply determine lake evaporation. Yes or no? If you have the value of all the other things, you can simply find lake evaporation. Yes or no? This is your water budget. Nothing tough in this. Okay, delta is change in storage. So if you simply want to find lake evaporation from here, lake evaporation will be P plus VIS plus VIG minus VOS VOG transpiration plus delta S. All these terms will come here. This minus CL will go there. So you will get this final equation. Okay. So with the help of this equation, put all the other values, put the volumes of all the other things, and simply get the lake evaporation. But this will give you the least accurate answer. Okay. So this is simple water budget equation. I hope this thing is clear to you. Now we'll continue tomorrow. Okay. We will continue tomorrow, and in tomorrow's class, basically, we will discuss evapotranspiration. What is evapotranspiration? What are droughts? Aridity index. We have different topics tomorrow, so we'll discuss them in tomorrow's class. I hope you have enjoyed today's class and you have understood the concept today. So basically, in tomorrow's class, we are going to discuss evapotranspiration. Tomorrow's class will be basically focusing on evapotranspiration. And yes, one more thing. Tomorrow is Saturday, but still, I will try to take class because on Holi we don't have there was holiday, so I will try to cover that class tomorrow. Okay, so on Saturday we will have class, that is for sure. I will make sure that tomorrow there is class. If it's not so, you will get to you will be notified. But yes, as of now, tomorrow there will be class. So let's end our class today. So thank you everyone. Stay blessed, take care, and keep solving and revising everything so that you become perfect champion this one. Okay, so take care everyone. Good night.